Hi there, Miss Barber again. Example, the Acme Food Company requires that its soup containers or cylinders with a capacity of 64 cubic inches and be made of aluminum. What radius and height will use the least amount of aluminum? Circle the word least. Let's begin by drawing a diagram. A cylinder can will have a circular base and a circular top. We'll connect the two sides, so now we have a drawing that looks a little bit like a cylinder can. Let's mark the center at the top circle and indicate that the distance from the center to the side of the circle gives us the radius. Now we have R for the radius. Let's proceed to look for the height of the can. That would be from the top to the bottom. And that measurement we will call H. I think we've got relevant variables, so let's list some constants and constraints. We are given that the volume has to be 64 cubic inches, and the formula for the volume of a cylinder is V equals pi r squared h. So the formula for the volume and the constraint of 64 have to be equal to each other. We write pi r squared h equals 64. Now let's just go ahead and solve for h. The height would be 64 divided by pi r squared. Our objective here, since we want the least amount of aluminum, is to minimize the surface area of the cylinder. So how do we compute the surface area? The surface area will consist of two circles, the top and bottom, so we need 2 times the area of a circle, plus to go all the way around, it's going to be the area of a rectangle. The rectangle will have a height of h, and the width is going to be the circumference of the circle. Let's replace those words with letters. S would be equal to 2 times pi r squared, that's the formula for area of a circle, and for the area of the rectangle we've got the height, and the circumference of the circle is 2 pi r. We need to decide in which variable do we want to solve this, r or h. And previously we already solved for h in terms of r, so let's do the surface area. S of r is equal to 2 pi r squared plus, and where h was, let's replace it with what we said equal to before. 64 over pi r squared, and still multiply by the circumference. We can simplify by canceling the pi's and one of the r's, and now we get our objective function. S of r is equal to 2 pi r squared plus 128 divided by r, provided that r is between 0 all the way to infinity. R cannot be 0, that's why it is not included, because it's in the denominator. We are now ready to find the extrema. To find extrema, we always first find critical values, and critical values are where the derivative, in this case s prime, equals 0, or s prime, the derivative does not exist. Let's find s prime. The derivative would be s prime of r is equal to the derivative of 2 pi r squared, bringing the 2 and the power down and multiplying it to the 2. That's the coefficient. You get 4 pi r minus, then you have the constant 128. The derivative of 1 over r is negative 1 over r squared. Since r equals 0 is not in the domain, we are not concerned with where the derivative might not exist. We still need to solve for where the derivative equals 0, so we'll set our derivative function equal to 0. 0 is equal to 4 pi r minus 128 divided by r squared. Let's solve for r. I will add 128 divided by r squared to both sides. That will give 128 over r squared equals 4 pi r. And then let's multiply the r out of the denominator. So we're going to multiply by r squared on both sides. That's going to get to 128 over 4 pi equals r cubed. So notice I divided by 4 pi on both sides, multiplied by r squared on both sides. Then we can reduce 128 over 4. Let's simplify the 128 over 4. That'll lead to 32 over pi, and that's equal to r cubed. We'll take the cube root of both sides to get r by itself. So r is equal to 32 over pi to the power of 1/3. That's the exact value. We can approximate that to approximately 2.17 using your calculator. The critical value is, we only have one, 2.17. Let's use the second derivative test to verify extrema. That is, we need to use the second derivative test to see if that critical value we obtained gives us the minimum we desire. The first derivative is s prime of r equals 4 pi r minus 128 divided by r squared. To use the second derivative test, you have to have the second derivative, so let's get that. S double prime of r is equal to, the derivative of 4 pi r is just 4 pi. Remember, pi is a constant, and the derivative of negative 128 divided by r squared, well, that's positive 256 divided by r cubed. Remembering that the critical value is 2.17, we need to evaluate in the second derivative our critical value. So s double prime evaluated at approximately 2.17, that's a positive number. Cube it, that's still a positive number. So the SIGN of the critical value evaluated in the second derivative, well, that's positive. And when the second derivative is positive, we know that the graph of the function is concave up. And if it's concave up, then the most extreme point in that area gives you a minimum. To use the least amount of aluminum, the radius should be 2.17 inches, and we were also asked to solve for the height. And the height, the formula we got for that earlier, 64 over pi r squared. We'll put in 2.17 for the r, so 64 divided by pi times 2.17 squared. Your calculator will give you an output 4.3262400251. We'll round that to 2 decimal places, and we'll have that the height of this cylindrical can should be 4.33 inches.